The first speaker, Dr. Weiming Huang from Leeds University, is a lecturer in urban data science. He's also on the local organizing committee and helped us here in Leeds with the organizing and selecting the program. And I'm really excited to see what he's having to present to us. He was previously at University of Singapore, comes here via way of Sweden, and today is actually his first day of the second year at Leeds University. So please welcome.
Thank you very much, Dennis, and good afternoon. I'm very happy to have this presentation with you at this conference. So as Dennis just said, that I have a mixed background in GIS and in computer science, so that I do very technical stuff for geospatial data. And so I had my PhD from Lund University in Sweden, and then I went into a pure computer science environment at Nanyang Technological University in Singapore, where we developed some of the where we had some early endeavors in developing geospatial foundation models. So let's, I'm going to show some of the examples that we had. So I know that, foundation model is a buzzword now, so I'm going to first quickly introduce this. So a foundation model is a machine learning that is pre-trained with very large scale data sets and unbridled computing powers to gain a very general contextual understanding of the patterns, structures, and the representations from the large amount of data. Also another key characteristics of a foundation model is that it's not task specific. It can be used for a wide array of tasks. So it's different than the conventional task-specific machine learning models. So now we have seen foundation models in different forms and also developed for different data modalities. So for natural language, we all know that there are GPT family models, some others. And for computer vision, we have many famous models that could generate the text-to-image generation models and sometimes the image representation models. And for vision language, this kind of multi-modality model, there are, this is also very popular. We have CLIP, BLIP. Also a very popular research direction. And also that there are some embodied AI foundation models emerging, like PalmE for robotics. So, and in this context, the foundation models have also sparked great interest in our geospatial data community. And so earlier in this year, we published the paper, with the title Geospatial Foundation Model. How will GeoFoundation model reshape spatial data science and geospatial artificial intelligence? And in that paper, we had a definition for what is a geospatial foundation model. So it is a geospatial foundation model. It's trained or pre-trained on heterogeneous spatial temporal data. It's capable of reliably performing advanced spatial temporal reasoning and designed to incorporate spatial, temporal, and other contextual factors into their output. And it's designed to support a wide range of geospatial downstream tasks in geography and neighboring disciplines that benefit from a spatial or geographic perspective. And we revealed many existing works in this field, and we found that the existing geospatial foundation models were mainly developed in two forms. The first one is those generative models which can generate either language output to answer some geospatial questions, or some or some images like generated maps or something. And there also is another major stream in the development, which is called representation models. So actually representation model. So in this presentation, I will mainly talk about representation models, which is getting increasing popularity for the realization of geospatial foundation models. And so what is a representation? It's a very broad word, right? But the word representation has some specific meanings in machine learning. So representations in a machine learning world, they are also called embeddings. They are the way that machine learning model understands the world and other internal language of machine learning models. So to give a formal definition of what is a geospatial data representation learning, that given geospatial data in different modalities like points of interest, like human trajectories. So the goal of learning geospatial representations or embeddings is to learn a mapping function from the data to generate low-dimensional embeddings of each geospatial entity or each location. So what is really an embedding? An embedding is actually a d-dimensional vector composed of real numbers. So for example, in a foundation model or in a machine learning world, so it could, the embedding of a grocery store, a geospatial entity, could be something like, minus 0.5 or something, and until the dth dimension. So this is the internal representation in a machine learning. The machine learning model's internal representation or embedding for this grocery store, and it can be generalized to anything, to any geospatial entity or geospatial location. And subsequently, because that the embeddings, they entail very rich information pre-trained from the data, from the geospatial data that were used for pre-training, like the trajectories, remote sensing data, like points of interest, like OSM, like everything, because they are so informative, they are so enriched, that so they can be used for various geospatial analysis, like inferring land use, house price, population density, traffic pattern, or something. So as a very brief summary of the characteristics of geospatial representations. They have two key features. One is that the features, the embeddings, are pre-trained in a self-supervised way, so that we just mine the data. So the data was pre-trained, not relying on the ground truth data of a particular downstream task. So for example, we don't use the ground truth labels of land use, of traffic patterns to train the model. It's just about the data, the huge volume of data. And then the second characteristic is that because they are not pre-trained on a particular task, so they are general enough so they can be generalized to different types of tasks. So we all know that foundation model pre-training requires large volumes of data. So where can we find the data? Of course that we have so many data sources, right? Like remote sensing images, like human trajectories. But then, and we saw that OSM is a suitable data source for pre-training geospatial foundation models. It is a great wealth of internet-scale geospatial data for pre-training the foundation models. Then, to this end, we developed a preliminary version of city foundation model, CTFM for short, that uses a variety of geospatial data types in OSM, in the entire OSM of a city for pre-training. So we recognize that the OSM mainly has three major data types. The first one is node, like points of interest. The second one is way, like road segments, buildings, airports. So actually all the polygons are organized as ways in OSM. And the third type is relation, like bus routes, like train lines. And we try to utilize all of them to train a foundation model. That so how we trained the model? We had a fundamental principle of for the pre-training that for each entity, for each OSM entity, like a building, a point of interest, we see its information from three perspectives: visual perspective, textual. Visual perspective here it's mainly pertaining to the shapes, and the textual perspective, like the annotations, the types, the categories. Locational, is about how, where are these entities, and then the idea is to maximize. So that's about how to train the model. So during the pre-training, we maximize the mutual information between these three information perspectives, so that different information perspectives can mutually enhance each other and can mitigate the missing information which is prevalent in OSM, like missing annotations. So, for example, the machine learning model would, the foundation model would know that this kind of, a building of this kind of shape is likely to be like a residential building, although the annotation is missing there. So that's just one example, and on another level. So that was for each entity. On another level, for different entities, we designed the model to let each entity inform other entities, so that the information of a road segment does not only contain the information of this segment. The information of other entities is also propagated to its embedding, like including the nearby points of interest, buildings, bus routes. And for each building, it does not only have its own features like shape, like coordinates, like annotations, but also the representation contains information from the nearby points of interest, nearby buildings, and the nearby road segments. And for each region is like a land parcel or like a small scale grid in an urban area. So for each region, it contains everything in it, like buildings, points of interest, road segments. So that's the fundamental design principle is that everything informs everything else. So the embedding of one thing also contains other things. So we found that after this pre-training, the embeddings of from CTFM makes a lot of sense. That if we only use a pure language model to generate embeddings for the entity types, then it believes that amenity hospital is similar to amenity cafe, amenity restaurant. But for our CTFM, the embeddings, they make more sense. Like the hospital is more similar to clinic, to doctors, to pharmacy, because then it really captures the semantics of the urban areas. Since that we have kind of embeddings for everything in OSM in a city, so we can do many tasks, right? So we tested the model in Singapore, New York City, and Seattle. So for each building, we used its embedding to infer its building function. For each road segment, we use embedding to infer average traffic speed. For each region, we infer the population density. It's also very interesting to observe that although that OSM is very static, there is basically nothing, no information about traffic in OSM. But if you have a very good representation of the built environment, so that you could potentially also, they could also potentially facilitate some traffic-related tasks. Okay. So I'm conscious of time, and then later we extended the research to build another foundation model. Dedicated to the road network, which was published in Europe last year. That we use in this study we use the street view images to enrich the embeddings of the road segments. So then the performance for the road level tasks, like traffic, like the road function, is greatly enhanced. So at the very last, I would also like to introduce one of our endeavors in generative AI, that we know that the large language models, they are very good. They are very capable in answering many questions. But they are not so good in answering very fine-grained place retrieval questions, and they lack spatial awareness. So for example, just 1 minute, and I tell ChatGPT, I'm here with this lot and long. Can you give me the closest McDonald's? And probably ChatGPT doesn't know this because this is too detailed. And then we saw that it would be useful if we could communicate with map services directly using natural language questions. So that we then trained a LAMP, the model, a model called LAMP. It's an acronym for a language model on the map. And this model is trained with OSM POIs, and is capable of answering the questions like, I'm here with this lot and long, and please recommend some nearby food options. Find the closest McDonald's, that is even open at this time, and plan a trip in Singapore for 3 days. And thank you very much. That's my presentation.
Oh, wow, that was amazing. Guess it became clear that I'm never going to be a doctor, and I'm quite happy that I finished university before large language model were a thing. I'm sure many of you will have a lot more smarter questions than me. And I mean, for me, what I realized there was like Tober's first law of geography, like things that are near in geography, whichever dimension they are, they're more likely to be like each other than things that are further away. But yeah, probably the smart questions. Ian?
I noticed that your city models were New York, Seattle, and Singapore. They're all quite modern. You didn't pick any European cities with sort of a medieval history. Is there a reason that they doesn't work there, or you just didn't fancy looking at them?
So those three cities have very good data availability. So that's the number one reason. But I think so that's maybe the only reason. It's not only about the pre-training data set, like points of interest, like like OSM. It's also about the availability of ground truth data for testing, like land use, like traffic speed. But it's not so available in Europe. And also another question that maybe I could mention is that because I got this question for a few times, that for this CTFM, we didn't train this in a global scale. We trained, you know,
It's trained on a specific
it's trained on a specific city. Yeah, so that we just picked such examples. Yeah.
Yeah, so for predicting things like traffic speed, are you taking the embeddings that you get for the road segments from the foundation model and then putting some other simpler machine learning model on top, like some kind of regression or classification model to then classify based on the embeddings and some training data of some sort? You know, this is a 50-mile-an-hour road, or this is a 30-mile-an-hour road. Is that the kind of approach you take there?
Yes, yes, exactly. That I mean, it's and we use. I can't remember that random forest or logistic regression that we I mean then we used a handful of ground truth data to train the shallow predictor that we and to use the embeddings. Yeah.
And what was? Can you just go forward to the slide about the road embedding model? What stuff were you putting into this road embedding model? It was a bit later on. I didn't quite.
Yeah, this one.
Yeah, the previous one to that. So this gives you an embedding per road segment.
Yes.
Right. Okay.
And in this work, we used the street. I mean, we didn't only use the spatial proximity, as Dennis said that it's the first law of geography, and we also used what now is called the third law of geography. That if the configuration or the environment of two entities are similar, then their properties are also similar. So that we use the street view images from Google to capture the configuration. I mean, the similarity of configuration of the environments. Yeah, and then we enforce the foundation model to learn that. I mean, perhaps these two road segments are further apart, but their environments are so similar, reflected from the images. So then their embeddings should also be similar. Yeah.
Thank you.
So there's like various tools for, like for example, with like satellite imagery and being able to say like, we think this is a building. Like, does it look like a building? Can we add it to OSM as like a vector, like building outline? And I'm wondering if like you could essentially do something similar with this, where you have quite good predictive, like you can say this building is probably like a doctor's surgery because it's very, very similar to all the other doctor's surgeries. And I'm wondering if there's some sort of like, you could basically wrap this up in a tool that could be used to improve the quality of like OSM data.
Yes, that's kind of our motivation,
Okay.
one of our motivations, I would say. And yeah, there is a huge potential to do that, although that it's not perfect, and and it's probabilistic, and yeah, and you know, we are, we propose such methods, and if the OSM community people would like to adopt some of the research, some of our methods, and we would be more than happy to help. Yeah.
We have time for one last question. Over there, I can't read your name.
I'm Sarah. Yeah, it's very interesting. I'm concerned because within the global south in particular, the automatic recognition of buildings is terrible, like really still quite bad.
Yeah.
So I'm curious whether you've tried this at all in the global south, and there's also the question of the joy of OpenStreetMap is that you'll get one person who absolutely loves mapping their neighborhood, and so you'll have their neighborhood mapped in exquisite detail. This is my husband's role in our relationship. So I'm curious about if you're concerned that you're going to sort of overtrain on particular areas where you have excellent quality data. Heidelberg, Germany is beautiful, and our suburb of London is terrible, and I don't, so you'll have, how do you correct for that, or make sure that the sort of massive overmapping of certain areas, which has nothing to do with the actual structure, it has to do with where OpenStreetMappers live. How do you correct for that?
Yeah, so that's a, I mean, that's a great question. And I mean, for now, I mean, as I just mentioned, we train city-specific models, like, so that actually, so that models in different cities, they don't interfere with each other, and so that a pattern in Singapore wouldn't really affect a pattern in an African city. So that's also one of the motivations that we did it in this way. But also in some of our experiments, I mean, maybe it's just us, that we found that if we train like a somewhat global model with multiple cities, it didn't really help. So maybe that it's that the intrinsic underlying logic of different cities are just so different, and the model could be confused. And also, perhaps the reason is also that our models are not big enough, are not large enough, and it doesn't have the brain to remember everything. So that, so I would say that if the model, I mean, perhaps if the model is super large enough, then it would be able to distinguish, you know, different patterns, you know, the global north, global south, you know, and it wouldn't mix them up. And yeah, I'm just guessing this. But what we are doing now is like we train specific city models, and sometimes we mix like 2 or 3 cities, but for a global level model, we are still not sure about that. Yeah.
Thank you very much, Dr. Weiming. Huang.